Now things are a little jumbled, a little out of order on the board. We came down to here, and then we came up to here, and then we came down to here. Well, this is the next place we're going to go, and then we're going to do this. So, the question now is, are the vectors v1, v2, and w1 linearly independent? Now, the definition of linear independence is that if you have a set of vectors, the usual definition is the one we're going to use here, but I'll give you a couple of alternative definitions that maybe have a little more meaning. Simply means that there's no vector in that set that's a sum of multiples of the others. You can't combine any, take any vector in the set, you can't combine the other vectors to get that one. Okay, that vector is not in the span of the rest of the set. So no vector is in the span of the rest of the set of vectors. So W1's not in the span of V1 and V2, V2's not in the span of V1 and W1, V1's not in the span of V2 and W1. Not if they're linearly independent. If any of these vectors is in the span of the other two, then every one of these vectors, it turns out, is in the span of the other two. That's not hard to prove. And the vectors are not linearly independent. Okay? And there are other definitions. Look at the document. You see a couple of other ways of saying it. The equivalent condition, completely equivalent to saying that any of these vectors is in the span of the others, if it's not linearly independent, and that no vector is in the span of the others if it is. Okay, so no vector is in the span of the others is equivalent to saying that C1 plus C2, C1 V1 plus C2 V2 plus C3, in this case we call it W1 because that's the way the vectors were noted. Okay, this sum is equal to the zero vector only if C1, C2, and C3 are all zero. Now, clearly, if C1, C2, and C3 are all zero, you're going to get zero here. So I don't mention that part of the condition, although probably I should. But the key is that the only way this can give us zero is for all three C's to be zero. Okay? Now, this equation, if I substitute the vectors V1, V2, and W1, and it's not W1, I'm sorry, it's W3. W3 being the vector 2, 3, 4. Okay? If I use W1, well, we'll see. So, okay. If I plug V1, V2, and W3 into this equation and do the simplification, I get a set of simultaneous equations that can be expressed as a vector equation you see here. Now the vectors, just as you had the 3, 2, 4 vector here, it appeared here, and the negative 2, 1, 5 vector appeared here. Well, when you plug in the V1, V2, and W3 vectors, the V1 vector is going to appear in this column, the V2 vector is going to appear in this column, the W3 vector is going to appear in this column. Now don't take that as a rule, don't do that, think this through. Otherwise, if you don't keep reminding yourself, you're going to do something you shouldn't do if you don't bring it all the way back to this equation and its simplification. It's easy to do that. You've done it a few times. You know what to expect. But it does give you these vectors in the column. And it's doing then this matrix times C1, C2, C3 equals 0, 0, 0 vector, which is the zero vector. Okay? So this equation by this process leads to a set of simultaneous equations that can be expressed as this matrix equation. Okay, you understand that. You've done that. I think everybody sees that, or everybody is at least in a position to think about it for a minute and understand it. There's the matrix equation. Well, that matrix equation has the form AX equals B, with the added condition that B is 0. So we can say that's this is a matrix equation of the form AX equals 0. A is a square matrix. If A turns out to be non-singular, then we can solve this equation very easily. We just multiply both sides on the left by A inverse. A inverse times the 0 vector. Well, the 0 vector has all zeros. Any matrix we multiply by a column of zeros, we're going to get the 0 vector. So A inverse times the 0 vector gives us the 0 vector. A inverse times AX gives us just X. And what's X? X is our vector, column vector, C1, C2, C3. Because, of course, here's A, here's X, and here's B. Okay? X is this column vector. So the column vector is going to be the inverse of the A matrix multiplied by the 0 vector. Now this is provided A is non-singular, and we haven't yet established that. But I'm saying it's got to be so. And thus V1, V2, and W1 are linearly independent because we just found that C1 has to be 0, C2 has to be 0, C3 has to be 0. Again, assuming A is non-singular, invertible, determinate non-zero, equivalent. So the question now we have to establish, does this argument hold? Is A in fact non-singular? Well, I'm claiming that the determinant of A isn't 0, so the answer is yes. You can verify that. Very easy to find that determinant. And it follows then that V1, V2, and W3 are in fact linearly independent. Again, this matrix equation, since this matrix has non-zero determinant, it's invertible, which implies that C1, C2, C3 are equal to the inverse matrix times the 0 column, and any matrix times the 0 column is a 0 column, so C1 is 0, C2 is 0, C3 is 0, just as we say up here. Okay, so that's kind of neat. And it's actually a fairly simple test for linear independence, but you have to understand the definition of linear independence and what it means in order to apply this to vector spaces. Okay, and our paradigm vector space would be R3, our three-dimensional space, X, Y, Z, vectors in the plane, vectors in space. What this is saying is that you got the vector V1 in some direction, you got the vector V2 in some other direction. Okay? Now if you start combining V1 and V2, it turns out that you get vectors in the plane that contains the two vectors. Okay? So vectors in this plane, if W1 is in the plane, then you can add multiples of V1 and V2 to get W1. It's not W1, it's W3. You can add multiples of V1 and V2 to get W1, can't you? Okay? And that tells you that W1 is in the plane defined by V1 and V2. W3, on the other hand, gives you, combined with V1 and V2, gives you a linearly independent set. None of these vectors is a linear combination of any of the others. Okay, any vector in the plane of V1 and V2 is a linear combination of V1 and V2. So W3, not being a linear combination of V1 and V2, is not in that plane. So you have two non-parallel vectors forming a plane and a third vector out of the plane. And it turns out then that with these three vectors, we can form any vector in three-dimensional space, as we're going to see in the next video, I believe.